All right, good afternoon, everyone. Let's continue, and I'll pick up the pace a little bit more today. Okay. And as we go along, feel free to interrupt anytime you have any questions. Right, I'll be taking periodic breaks every few minutes. But in case I'm moving too fast, you need a little bit of a break to actually understand the concepts. Feel free to ask. Okay. All right. So we did. Besides, let's begin today here. I think we spoke about what a voltage source and a current source is. An example is shown right here. A battery is an example of a DC voltage source, right? There's DC and there's AC. So battery, any kind of battery, the coin cell, AAA, AA battery, C cells, D cells, all of those are examples of DC voltage source. The batteries inside your mobile devices, your laptops, they're all DC voltage source. There are some chemicals in there and electrochemistry or electrochemical reactions take place. And there's a difference in electrical potential between the output terminals. The value of that voltage at the output terminals remains constant, and hence constant voltage source. Okay. Now, DC power supplies, like the ones that are shown here. So I'm going to note any battery is a DC voltage source. Okay. Now, most power supplies, as we spoke about last in the previous slide, can be configured to run in constant voltage or in constant current mode. Right. So I pointed out the benchtop supplies that we have in the lab benches behind us. And so those all can run in constant voltage or constant current mode, CV and CC. It's hard to see on this model, but like right here at the top, somewhere here, it'll show you, actually, I believe it's this letter right here. It shows you CV or CC. Now, these are different make and model. These, I believe, are Keysight or Keysight instruments. We have these Regal instruments in most of the labs, whether it's E lab or CP lab. These were upgraded a few years ago, and so these are all Regal models. And they can run in constant current or constant voltage mode. So voltage or current. Okay. All right. Then a couple of other examples of exponential and logarithmic functions. Semiconductor diode is a two-terminal device that is the most fundamental of semiconductor devices. Okay. The name diode itself comes from the fact that this was a solid state or semiconductor version of a vacuum tube diode. Okay, so a vacuum tube diode would be like a cylinder, glass cylinder, which has vacuum. This is just for explanation purposes, okay? And so you have this glass cylinder, and you had two electrodes inside this cylinder. All right. And there would be a cathode, and there would be a filament light bulb in there. Let me make it more. It's a filament. That's the cathode, noted with a K. And then there's a plate at the top, known as the anode, noted with an A. So A and K. Now, if you've studied chemistry, you may be familiar with these terms, right? Electrodes, sometimes labeled as anode and cathode. So a vacuum tube was the first electronic device. Okay, it was the first electronic device. And this was way back in the 50s and the 60s. All right. They are kind of making a comeback. And so there are some high-end audio equipment that actually use vacuum tubes to design electronic circuits. Anyway, so a quick understanding of this will help. There's this vacuum tube. It's about the size of a human thumb, perhaps. Depending on the application, of course, tubes can be small or large, but typical vacuum tube, size of a human thumb. And you have two electrodes in there. One is the anode, the other one's the cathode. Now, there is a filament that is right underneath the cathode. It's a heater filament, and it heats up. It heats up that cathode. When it reaches a certain temperature, depending on the make, model, and the material that's used to construct that electrode, they start emitting ions. And they kind of float on top of the surface of the cathode. They impart enough energy to the atoms of the cathode that there are electrons that come up and float on top of the surface. They are now free to move. Okay. What charges do electrons have? Negative charge. So if you take this anode and you connect it to a power supply with a positive terminal at the top connected to the anode, negative to the bottom, what happens? Or what do you think would happen to those electrons? Anyone? Opposite charges attract or repel? They attract. So you have a positive here. What do you think will happen to those electrons? You just gave me the answer. Opposite charges attract. You have a positive terminal, positive charge at the anode. Electrons are negatively charged, so electrons are attracted towards the anode. They go towards the anode, combine, and they start moving in this direction. So electrons start flowing in the circuit. Now, conventional electron flow, electric circuit or electric current flow, we always say is the opposite of the flow of electrons. If the electrons are moving from left to right, we say current is moving from right to left. And so in this case, the electrons are moving in that direction. The current is said to be moving in that direction. Okay, so there is current flowing in the circuit in a counterclockwise direction. Well, just because of the circuit schematic. If I moved the voltage source on the other side, it doesn't change the circuit at all. It would just be like a clockwise direction. It doesn't really matter. Okay, so this was the first electronic device. The name came from the fact that it had two electrodes. Diode, two electrodes. If you insert a third element in there, third electrode in there, it becomes a triode, three electrodes. Fourth, quadrode, pentode, hexode, so on and so forth. So it was a way of controlling the flow of electrons. Right now, it's a very simple thing. You attach a power supply externally, and you're just permitting the current to flow through. But if you add a third and a fourth and a fifth electrode in there, you can control the flow of that current, okay? Which is something you will study in 315. So this is the vacuum tube diode. As I said, two electrodes. When scientists and researchers created the semiconductor version of this device, they carried the name over. Hence, the name of the semiconductor device is also a diode. That's where the name comes from. Despite the fact that the actual PN junction diodes nowadays, they don't have any electrodes in them. Okay. Even the terminal names, anode and cathode, are carried over. So the diodes, I believe you have diodes in your lab kit. Yes? Yes or no? Yes, right? So those diodes have terminals, and those terminals are still labeled as anode and cathode. So even though technically they are not electrodes anymore. The symbol for a diode is an arrowhead, or a triangle, if you will, with a 90-degree line, or a line at a 90-degree angle at the tip of that arrow. This end is the cathode. This end is the anode. And on the real life diodes, if you look at the tiny cylinder, the packaging, there is a band that runs around the periphery. That band is close to one terminal than the other. The terminal that is closest to that band is the cathode. On a 1N4000 series, it's a black epoxy packaging, so there is a gray silver band. On like plastic transparent packaging, that band is more often than not black in color. And those, again, those bands indicate that that terminal is the cathode. All right, let's take a pause. Let me know if you have any questions. Yes. So there are two, I wouldn't say classifications, but there are two ways to look at current flow. One is known as the hole flow. The other one is known as the electron flow. And both of them are the opposite of each other. And so for conventional purposes, we take current flowing as opposite of the flow of electrons. There's also books where they use electron flow, meaning currents flowing the same direction as electrons. But for the most part, it's been typical convention to use a hole flow. Electrons and holes are something that you'll learn in semiconductor theory in EE 315. Essentially, just in short, I'll explain. I have you. When an electron moves out of its spot from an atom, leaves behind an ionized atom, right? But when an electron moves out, what is left in the actual spot where the electron was? An empty space, empty spot. For lack of a better term, scientists and researchers agreed to call it a hole, H-O-L-E. It's an empty spot, it's a hole. And so holes are the exact opposite of electrons. It's not a physical device or a physical quantity per se, but it's a particle in its own right. Okay, so electron is an actual subatomic particle. A hole is a representation of the absence of an electron, but for theoretical analysis, we treat that hole as a particle in its own right with positive charge. So if we follow or use the flow of electrons as the current flow, we say it's electron flow. And if we use the opposite, it's hole flow. Yes. So question being asked is, how do the electrons become separated? That's a very good question. Again, it goes back to semiconductor theory. So, and we are kind of going into a tangent into 315 a little bit, but we have atoms, right? Atoms have electrons that are orbiting the nucleus. That's the Bohr's model and the Rutherford model of an atom, right? And of course, there's a different branch of physics that deals in string theory. So we leave that on the side. But the structure of an atom is such that it has a nucleus. The nucleus has protons and it has neutrons. And then you have electrons that are orbiting in specific orbits around the nucleus. So now they have energy, right? There's a force of attraction between the nucleus and the electrons that keeps it bound to that atom. But as you get further away from the nucleus, these electrons sometimes obtain enough energy from external sources that they are ripped away or they are free to leave that orbit. And so when we heat it up, there is thermal energy that is imparted to that cathode. And the electrons that are on the outermost orbit, they acquire sufficient energy from that thermal heat, and then they're able to free and move. It would not happen with all materials. It will only happen with specific materials, right? We can heat up wood all we want. It's not going to become a conductor, right? Or you can take any insulator. You could heat up ceramics or any kind of insulating material, like glass, for instance. It's not going to impart sufficient energy for electrons to actually break their bonds. So they will never become conductors. Okay, yes. Because it has, so the question being asked is, why is it a diode? So di, in this case, Di represents 2. And so because it has 2 electrodes, one is a cathode, the other one's the anode. So 2 electrodes, diode. A third electrode would mean 3 or tri, so triode. And then we have quadrode, pentode, hexode, and so on and so forth. Beyond a certain number, it's simply, they simply call it a 8 electrode vacuum tube or a 9 electrode vacuum tube. I've never seen one in real life. I mean, like higher number of the long time ago when I was a student, I think maximum I might have seen was 4 or 5 electrodes in the vacuum tube. Even that would be hard. It'd be hard pressed to find a real vacuum tube right now. But in literature, and I've seen images where you have like more than 10 electrodes all crammed in. So even if you just do an internet search, you should be able to come across like images where you can see electrodes vacuum tubes with multiple electrodes. Okay, coming back to our topic. The reason we're talking about the diode is it's the most fundamental of semiconductor devices. The relationship between the voltage and current for a diode is not linear. Okay, for a resistor, we say the relationship is linear. Resistor, capacitor, inductor, the relationship between the voltage and the current is linear. As voltage increases, current increases. If it decreases, right? But for a diode and a transistor, FET, BJTs, the relationship is non-linear. And for a diode, this is known as the diode equation. Okay, and you can see the diode equation represents the diode current, and it's approximately given by the exponential, the exponent of the diode voltage V. Okay, so the current of a diode or even for transistor depends on the exponential function of the voltage across that diode. Okay, and hence we're talking about exponential and logarithmic functions. So that's something that, again, you will study in higher level classes. Yes. VT, so question being asked is, what is VT? VT is known as thermal voltage. Thermal voltage is something that is present in all semiconductors due to the temperature of the environment. Typically, it's in millivolts. It's 25.6 millivolts or less. And again, that theory is something that more appropriately belongs in like 315 higher level classes. Okay. Again, all of this is just an example of what kind of functions you can expect to encounter, right? Okay. Periodic functions of time. What do we mean by periodic functions? Well, if you have a quantity that changes its value at any given point in time, but it repeats itself after a certain time period, that would be known as a periodic function. Okay. all of AC power generation and distribution is sinusoidal in nature. Spelled like this and pronounced as sinusoidal. And short acronym we used is sine waves, S-I-N-E, sine waves or cosine waves. So it's just a sine wave. A sine wave is represented like this. Mathematically, we use the sine and cosine expressions, S-I-N and cosine, C-O-S-I-N-E. Okay. Like all AC power generation and distribution. So this is the form that our power outlet voltage would take if you were to measure it for a specific time period. And I'll explain in detail what each one of these terms means. Okay. So forget about the mathematical expression for now. All right. General knowledge question. What is the voltage and the frequency of our power outlets, at least in North America? It's a general knowledge question. Yes. 60 hertz frequency. Yes. And voltage, 120 volts. So if you look at your laptop adapters, your mobile phone chargers, any kind of device that plugs into a power outlet, any appliance, small appliance, large appliances, will have a spec printed on top, or there'll be a sticker printed on the panel. Okay. It'll say input and output. Okay. Appliance obviously is not going to have any output, so it'll only say input. But a laptop adapter or a mobile phone charger will have both an input, meaning you're plugging it into the power outlet. So it has some input coming in, and then there's an output that goes into your device. So it has both input as well as output. So if you look at those, it will tell you it is 110 volts, 120 volts AC, 60 hertz, and output is 5 volts DC. You can look it up right now if you have one. It's admittedly easier to look up a laptop adapter rather than a mobile charger, but it still is required by law. So all adapters, no matter where you buy it in the world, will have it printed right on top. Okay. Previously, it used to be that if you take a device like a charger outside of North America, or you bring something from outside of North America into America, you'd have to do an electrical conversion, meaning you have to change the voltage and the frequency. And you'd also have to do a physical conversion because the outlets are physically different. Okay. And again, whether you have been outside the country or not, this is something that you can look up very easily. The UK, the Europe, Asia, the European countries, Africa, Asia, they're all different. So, okay, physical connectors are all different. So back in my day, or just until a few years ago, we used to have to do a physical conversion as well as an electrical conversion. Now, if you look at your laptop adapters or your chargers, it will say a rating of power rating of input can range from 100 volts up to 240 volts, and frequency can be from 50 to 60 hertz. So you can use it anywhere in the world. You don't need to perform an electrical conversion. You only need to perform a physical conversion. I currently have a phone that I purchased from back home. It comes with a 120 watt fast charger. So it can go from 0 to 100 in like 20 minutes. But the prongs on it, I can use it in North America, but the prongs on it are circular. or cylindrical. So I can't plug it into a power outlet. So I have to have an adapter on there that converts it from, physically converts it, but it doesn't require any electrical connection or conversion. All right. And so I'll try and remember to bring it in next class just to show it. Okay. So physical conversion is required. Electrical conversion is not required for the most part. That being said, if you are traveling abroad anytime, you always want to check the power rating of your device. And output, of course, could be, let's just say it's 5 volts. So it's 5 volts DC and will state 1 or 2 amps capability. So this would be a 5 times 2, 10 watt DC charger. 10 watts is nothing nowadays, right? All right, so that's AC. So it says AC, which is alternating. Why is it alternating? Well, the value of the voltage of these power outlets in North America, it's, let's say it's 120, and abroad, let's say it's 230 or 240. The voltage is never constant, right? If you just plug in a meter in there and you try to do it, it's like it'll fluctuate between 110 and 120. But let's just stay with 120 volts, right? Even with 120 volts, what does that frequency mean? We have 60 hertz frequency. What does it mean? Well, Hertz was a German physicist and researcher named Heinrich Hertz, German or Austrian at the time. And that happens most, as it happens throughout history, he did some research about it and they honored him by naming the units of frequency after him. Okay, short for Hz, Hertz. What it means is the number of times that waveform repeats itself in 1 second. That waveform could be sine wave, could be a cosine wave, could be a square wave, rectangular wave, could be any kind of waveform or any shape, but it's a periodic waveform. Periodic means it repeats itself after a certain time period. The number of times it repeats itself in 1 second is defined as the frequency of that waveform. Okay, so a sinusoidal waveform that we see here will start from, so that's negative, that's positive, let's say that's 0 or the midpoint. It starts from 0, goes to a positive peak, comes back to 0. Then it goes negative, so it goes to a negative peak, and then comes back to 0. After this point, the waveform starts repeating itself. Okay, so the point where it starts repeating itself is known as one time period of that waveform. So this is defined with uppercase T. The lowercase t is exclusively reserved for time. Uppercase T is not time, it's time period. So there's a difference between time and time period. Okay. This is 0. I would also point out that 0 on the x-axis does not mean the beginning of time. It simply means the point in time at which we begin our analysis. That's all it means. Okay. 0 on the x-axis means the point in time at which we begin our analysis. So lowercase t is the time. It's a variable, because it could be at any number. And uppercase T is time period. Now, the inverse of this is the frequency. So inverse of T, 1 over T, is the frequency. It's basically how many cycles. So this is also known as one full cycle. This is known as one full cycle. Okay. And the number of cycles this waveform takes in 1 second is defined as the frequency of the waveform. So what did we just state? That the power outlet frequency is 60 hertz. That means that waveform goes up, goes down, goes up, goes down, goes up, goes down 60 times in 1 second. That's why it's 60 hertz. Now, if you were Dr. Strange and you had the power to slow down time, you could freeze time and you could see it. It goes from 0 to max, back to 0 to minimum, negative, come up back to 0. Do you think 60 hertz is fast? 60 times in 1 second, right? Seems like a really fast number, right? But in the grand scheme of things, larger overall picture, that's a very, 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 very low frequency. Most people my age can't even, well, I can't even hear probably below 100 hertz. Technically, human hearing is defined as 20 hertz to 20 kilohertz. So 60 hertz is technically within human hearing range, but 60 hertz is very, very low frequency. Consider the frequencies that we deal with in everyday life. What other frequencies do you think are around you? You have your mobile phones, you have your processors. What is the frequency of the frequency of the CPU inside your laptops or your tablets or your mobile phones? That's there, absolutely. But just in general applications, AM broadcasting stations, they operate at kilohertz range. If it's 640 AM, that number actually means that radio station is broadcasting at 640 kilohertz frequency. 101.7 FM stations broadcast as at megahertz frequency. So 101.7, the call sign, stands for the broadcasting frequency of that FM radio station. It broadcasts at 101.7 megahertz of frequency. Your wireless routers, microwaves operate at 2.4 gigahertz. Dual band routers operate at 5 gigahertz. Okay, so huge numbers compared to 60 hertz. 60 hertz is very, very small, very, very low, even though it seems very fast for us. All right, that's what AC is. Okay. So sinusoidal voltage, as I said, it's 120 volts. But in the technical definition, right here, we write it as A sine omega t, or A sine or A cos of omega t. Okay. Most functions are described either as sine or cosine. Okay. The electricity generated itself is a sinusoidal waveform. It takes the form of a sinusoidal waveform. Sinusoids are easy to handle mathematically. The derivatives of sinusoidal functions are sinusoidal functions. Any kind of waveform, whether it's square or triangular or rectangular, can be represented as a multiple of sinusoidal waveforms. Okay, so you can break down any square triangular wave and represent it as numerous sinusoidal waveforms. So what does this A stand for? The A actually stands for this peak right here. And this would be minus A. Okay, so the A stands for the peak value of the waveform. This is also known as the magnitude or the amplitude of the waveform. Amplitude of the waveform. Okay, so if we go over here, and it's asking the question, why is A equals to 170 volts? Why is it not 120? Right? So let's reflect on that a bit. The technical definition of AC is that it does not have a constant value with respect to time, meaning at any given point in time, its value is different. Yet we are putting one single number to it. We are saying it's 120. So if it changes its value at any given point in time, how can it only have one single value? Right? Well, what we are doing is we are trying to find sort of the average number, or a number that describes the average value of that waveform. So the peak value is different and the average value is different. Technically, it's not even average value, and I'll talk about that in just a bit. This, of course, is what we were talking about. Any kind of charger, this end is AC, this output is DC. We use diodes to rectify the AC signal into DC. Everything that we use in everyday life is more likely than not DC. Our laptops are DC, our consumer electronic devices are all DC. Every single consumer electronic device that we use, when you plug it into the wall, the first thing that is inside at the other end is a power supply. And the power supply converts the AC power outlet into DC, which is flat. The reason we do it AC is because it's very easy to transmit AC over long distances versus DC. Okay. So every single, the monitor, the projectors, all of the instruments that you see behind you, the computer, everything has a AC to DC power supply. A charger is the exact same thing. It's an AC to DC power supply. Not this one. There was, let's see, right here. Okay, I'll come back to the other two slides after we finish this one. So what is, if I have this waveform and it's half above and half below zero, what do you think is the average value of this waveform? Half is positive, the other half is negative. If I sum up and I find the average value of this waveform, what do you think it is? Zero, right? More likely than not, this average value should be zero. Yet, when you apply AC voltage or AC current to a system, it will carry energy. It will transfer energy into the system. So energy is being transferred and converted. Power is being delivered even by that AC source. So how can we mathematically represent, or how can we accurately represent it in mathematical equations? We can't use the average value because it turns out to be zero. So what they did was they decided, instead of taking the average of the waveform, of this waveform, we will first square the waveform. So if you have this voltage, and this voltage is described as a function of time, right? Because the value of this voltage changes at any given point in time. So this quantity, or this function, is described as V of t, voltage as a function of time. Instead of finding the average value of this function, we will first square the function. Then after we have the square of the function, then we will take the average of the function. Okay. And so to average it out, we integrate it from 0 to t. Integration is nothing but summation of all slices under the curve, right? So we integrate the waveform for one single time period. One single time period, we integrate the waveform. We sum it up. So we have all of the values of that waveform for all period, for that one time period. And then we divide by t. Find the average. But now, This is not the average of the waveform. This is the average of the square of the waveform. Because we took the square at the beginning, now we will take the square root of the result. And then this value is known as the RMS value, or the root of the mean of the square of the waveform. Root mean square, more commonly known as RMS. Okay, RMS. Let's take a pause while all of that sinks in, and let me know if you have any questions. Yes. Okay, so the question being asked is this known as the average value? The correct response would be not quite. I know I began my explanation by saying what is the average value, but that was for explanation purposes. The average value is something that is little different. That's the actual DC equivalent. In some sense, we can say that the RMS value is the DC value. But for the most parts, we keep the average value separate and we keep the RMS value separate. So RMS value is not technically the average value of the waveform. Okay, RMS value is its own quantity in its own right. And so we have, when we refer to AC waveforms, we say either the peak value or the RMS value. And coming back to our power outlets, for sinusoidal waveforms, our peak value is 170 volts, meaning the maximum peak value, not any number in between, just the maximum peak value. This is VP, which is approximately 169.169 point something. So approximately equal to 170 volts. So it's plus 170, and the lowest it would go is minus 170. And the 120 volts is a single value that represents the RMS value of that waveform. Okay, remember, it's 60 hertz. We just said it's very, very low frequency compared to everything else that we use, but 60 hertz is still fast, right? It's going up, down, up, down, up, down 60 times in 1 second, right? So if it's 60 times in 1 second, it's going from 0 to plus 170. Then it goes back to 0. That's only that's 1 over 1/20th of a second. And the negative half cycle, it goes to minus 170 and then comes back up to 0. And it does this entire cycle 60 times. So plus 170, minus 170. Total swing of 340 volts. If we take an oscilloscope, most oscilloscopes would be able to measure that kind of voltage. You are not going to do this in the lab. I'm just letting you know that it is possible. You could take an oscilloscope, you could take the probe, a 1:10 ratio probe, and stick it into a power outlet, and we can observe the waveform. Okay, we are not going to do that. Yes. So RMS value. Oh, so question being asked is what makes the RMS value more useful than the average value? So what I want to clarify is that technically RMS is not the average value because we reserve that average term for DC equivalence. But for learning purposes, I would say we take it as an average value. That's the average value of the waveform. Think of it this way. We have both a positive and a negative peak, right? Let's say we flip the negative peak, and now both of them are positive. So now we have, let's say they're all mountains of dirt. They're all positive peaks. Okay. Instead of positive, negative, they're all positive, positive, positive peaks. And there are mountains of dirt. And let's say you flatten them all out. Okay. You flatten them all out. So from here, you would have a waveform that looks like this. And if you flatten them out, you would get something like this. And this would be your RMS value. This would be your peak value. Okay. For most mathematical calculations and derivations, we use RMS values. If you are using a meter, they are all RMS. This is very important to remember. If you're using a meter, a DC multimeter, AC multimeter anywhere in the lab, or you're referencing an experiment, if you have only one single value, that means it's referring to RMS. If it's peak, it will explicitly state this is the peak voltage or a peak current. Okay. Everything else is an RMS. If it says 440 volts AC, that's an RMS value. But electricians who work on these power lines, they still need to know the peak value because, again, 60 times in 1 second, it's going to go to that peak value. So you need to have equipment that can handle that peak value, right? If you just take 120 volts as your peak value and you insert a device that can handle only, let's say, oh, it's 120, right? So I only need a device that can handle 140 volts. You stick it in there, it's going to get blown up. Why? Because at least 60 times in 1 second, it's going to go above 140 all the way up to 170. So it's important to know both RMS as well as peak values. Okay. And 2 minutes left. I'm going to quickly cover 2 more functions, derivatives and integration for capacitors and inductors. So unlike resistors, capacitors and inductors are energy storage devices. They're passive, meaning they can receive energy, they store it, and they release it back into the circuit at a later point in time. That storage time could be as few as microseconds or milliseconds. If it's an AC signal, it's constantly sending energy in, out, in, out, in, out, right? So inductors and capacitors are energy storage devices. The voltage and the current relationship is not linear. The change in voltage and change in current, yeah, that is linear. But voltage for an inductor is represented by L. And the equation is, and I'm going to write a very simplified form of this. Voltage for an inductor is the inductance times the derivative of the current, L di over dt. It's 2 o'clock, so if you have to leave, you can leave. I'm just going to continue recording for like just 1 extra minute, 1 or 2 minutes. So for an inductor, the relationship between the voltage and the current is given by this equation. Inductor voltage V is L di over dt. So the voltage is proportional to the derivative of the current. Remember, for a resistor, we had voltage was proportional to the current itself. V is proportional to I. The constant of proportionality was the resistance R, which is how we get Ohm's law. V equals IR. Here, it's proportional to the derivative of the current. So V is equal to di over dt. The constant of proportionality is the value of the inductance L. So V equals L di over dt. If the voltage and the current are functions of time, we write the equation like this. Time in brackets or in parentheses. So voltage as a function of time or current as a function of time. And then the subscript L simply indicates is an inductor. That's all it is. This equation and this are the exact same. No difference. Notations are different, but that's about it. And then finally, for a capacitor is the same thing. For a capacitor, the equation is capacitor current is equal to the capacitance and the derivative of the voltage. So I, current for a capacitor, is directly proportional to the derivative of the voltage. The constant of proportionality is the capacitance C. So I is C dV over dt, derivative of the voltage. All right. And then of course, if one quantity is derivative of the other one, you can flip it around. If you integrate the other quantity, you can find the other. And hence the equation for capacitor voltage is the integral of the current I. So we'll end class here today, and we'll pick up here again on Friday. I'll pick up right at these two slides. Okay, we'll begin here. We'll talk a little bit more about the equations, and then we'll take it more from here. So I sped up a little bit, but not as much as I would have liked. I should. Next class, we'll go a little bit faster than this.